cool. Okay, I think we're live. That's good. Uh, hey, so today we'll be picking up with logistic regression stuff. And we'll be talking about how to use it as a classifier, right? You want to classify, the data you have into, you want to predict whether it's whatever it is, right? So like, whether based on all these variables about cancer, whether or not the tumor is malignant, right? Or all these patient variables or whatever it is, you want to classify things as malignant or not. And if you have data about the actual outcome, right, then you can compare how well your model is classifying. If you know the truth, you can compare how well it's predicting, right, to how well, or to the actual values themselves. You can see like, oh yeah, we're classifying all the actually malignant people as malignant, and that's good, right? And the more data you have that actually, is predictive of malignancy, the better your model is going to be able to do at classifying. And we'll talk today more about like ways to classify and like ways to measure classification performance. You may have heard of ROC curves. That's a really good way to measure classification performance. And it's pretty common in, like biomedical sciences, and really it's common everywhere. It takes a bit of getting used to, but all you'll have to do is run it and interpret the area under the curve. But I do sort of motivate that with like what it actually represents. Cool. Let's see, hopefully y'all can see this. I wonder if I can make, that's fine. Cool, so if you've looked at the homework, let me think. Should we talk about, so in the homework, right, it's a really cool data set. It's about this scandal about graduate school admissions being biased. And it's really interesting, right? Like if you look at the data a certain way, it looks biased, but we're gonna see like if you can control for certain things, you actually get unbiased admissions. So it's an interesting case study of like why it's important to control for certain variables, but it involves an interaction, right? So I toyed with like putting this at the beginning of the slides or at the end. I might skip ahead to it if we're short for time, but I walked through an example that maps on pretty closely to that using the Titanic data set from lab. So we'll talk about that. We'll walk through an example of just logistic regression stuff at the beginning, but we haven't seen like an interaction or an interaction between two categorical variables, right? So we'll look at that because that matches pretty clearly or pretty closely what you do on the homework. Also, yeah, so like if you look at project 2, let me pull up, where's project 2? It's somewhere around here. Cool, so if you look at the instructions for project 2, right, you've still got a couple weeks. It's not like it's super looming or anything, but check it out, right? So if you look at the rubric, do a MANOVA, right? Do all those ANOVAs, t-test stuff. So the stuff from the first week of this unit. Then do some kind of randomization test. It doesn't matter what it is, right? Just do a randomization test. Do a linear regression, interpret the coefficients, plot the regression, check the assumptions, use robust standard errors and see if that changes anything. And then talk about like the R-squared, right? Then do the same thing, but then compute bootstrap standard errors. And you can resample rows, you can resample residuals, whatever you want. And then finally, well, not finally, but almost finally, this part is the logistic regression part, right? So you'll have a binary variable you'll want to predict from at least 2 explanatory variables. And you don't have to do the interaction, right? You can I just want you to have at least 2 predictor variables in the model. And it's just interpreting coefficients, right? Looking at a confusion matrix for your data, like, what proportion who were actually malignant did the model predict as malignant? What proportion didn't, right? Just the counts of like true positive, false positive, true negative, false negative. We'll talk about that a lot more today. Doing like a density plot, which we'll talk more about today, computing things like sensitivity and specificity. Then here's the stuff we'll talk about today, like the ROC curve, the area under that curve, which you can do using a package, right? You don't have to write the code yourself or anything. And then next week, we'll talk about cross-validation, which is really, really cool. But that'll be the last part of this one. And then regularization, we'll also talk about that. But pretty much like the moral of the story here is like, you've got more than 90% of this stuff already kind of under your belt. So, I mean, if you're bored and don't want to put it off, right, you want to make sure that everything's solid, it'd be a good time to go ahead and get started. Make sure you like have some data you want to work with. Again, you can work with data that you used last time if you want. You can also totally branch out, do something new, however you want to do it. Oops, crap. There we go, sorry. Cool. Yeah, let's just get started. Oh, so I just learned about an interesting function. This would have been helpful for some of y'all on the first project. And again, right, like I learned, like you're constantly learning new things when you're doing this kind of stuff, because someone's coming up with some cool package. So in the janitor package, there's this function called clean names, and it's neat, right? So it can take data that's formatted weirdly, right? So like if you might have run into a situation where you were trying to join based on an ID variable, right? And maybe, maybe for one it was Texas and it was capital T and one was lowercase t for the state name or whatever, right? So this function clean names is really nice because it makes everything lowercase and it strips out any sort of punctuation and it replaces them with underscores, right? So then they'll match up nicely and you won't have to go in and manually be like, G sub my underscore with a whatever, right? You won't have to do all that stuff manually. Oops, sorry, I didn't mean to click that. There we go. I was trying to find some tweets relevant to logistic regression, and one of the first things that came up when I searched logistic regression was this hilarious tweet. So hopefully you're not feeling like this person at this point. And if you are, that's fine. Like we'll do some review. I just thought it was a hilarious tweet. Anyway, so other people are feeling your pain too at this point, or maybe it's making perfect sense, right? Like it's weird. You got to convert, you're getting these log odds as predictions, right? And you want predicted probabilities. So you got to do all these conversions, right? And interpreting the coefficients is funny. Hopefully lab will help clarify some of those ideas, right? It's meant to like walk you through just the mechanics, right? Like how to actually think about these models. And I've asked questions that sort of probe that. So hopefully that's something that helps things click a little more. But let's do a full review, right? Let's do a full review of the biopsy example, except this time we'll use more than one predictor variable. Cool, so go ahead and grab worksheet 17. It's both on the server and on campus as well. And this is that same data set, right? It's got the outcome of the patient and then all these other measurements about a specific tumor they have, and whether it's benign or whether it's cancerous, whether it's malignant. Cool, and so you can read that in and just create a, create a binary indicator that's 1 if it's malignant, 0 if otherwise, just like before. And you'll want to go ahead and load LM tests because we'll do like coef tests today just to make the output prettier. Cool. So let's say last time we looked at predicting malignancy from just clump thickness, right? And we might have looked at like one other, but let's say we throw 3 variables in the model. So let's say we want to predict malignancy from clump thickness, and then from marginal adhesion, and then from bland chromatin. So 3 predictor variables, no interactions. We're just gonna, just an additive model and say data equals data. Make sure to say family equals binomial, right? So when you run a logistic regression, the only difference between that and a regular regression is the link function, right? So family equals binomial sets that logit link function, and make sure to say GLM instead of LM. Those are the only differences. Cool, and I'll just run coef test just so it spits out this output and not a bunch of other junk. You can do summary fit too if you want. Cool. So what does this mean, right? We've got these estimates. We've got this negative 10.5. We got this, it's close to 1.6, close to 1. So that's, remember, right? Like by default, it's in terms of log odds. So those are the coefficients, the linear coefficients predicting log odds. Log odds are confusing. It's better to interpret odds, right? So always, when you're interpreting logistic regression coefficients, and you'll see this like in any paper, people always exponentiate those coefficients. So then they can talk about odds instead of log odds, right? So just to illustrate this, here's these coefficients, negative 10, 0.95, 0.6, 1, right? We can take those and exponentiate them. So take E, Euler's number to that coefficient, right? We're just exponentiating them. Neat. And you can see they change quite a bit, right? Now they're on the odds scale instead of the log odds scale. So again, we can write this first equation. We can take those coefficients from this output, right? So negative 10.52, that's the intercept in terms of log odds, right? And 0.952, that's the clump thickness effect in terms of log odds. MA, the marginal adhesion, 0.601, that's its effect. And then 1.023, that's the, oh, sorry, that should be 0.025. Oh, it says 023. Whatever, the difference won't be that big a deal. I'll fix it in the slides before I post them. Cool. So those are just the individual coefficients, right? But this in terms of log odds. It'd be better to exponentiate. So take E to both sides. So exponentiate this, that undoes the natural log, right? And you're just left with odds. Take E to this side, and then use the product rule, right? You know that, E to the A plus B is the same as E to the A times E to the B, right? So you can rewrite it like that. It's a little easier. And cool, so there's the final equation in terms of odds. Interesting, right? So just compare those two for a sec. So this is additive. We're adding the individual effects to get the predicted log odds. But with odds, since we exponentiated, that's now a multiplicative relationship, right? So now we're multiplying the individual effects to get the predicted log odds, get the predicted odds. So for example, like just rewriting both of these. If you look at this intercept, right, the exponentiated intercept, think about what that means. This is giving us the predicted odds, right? If you want the intercept, that's when everything else is equal to 0, right? So imagine a patient who has clump thickness of 0, marginal adhesion of 0, bland chromatin of 0, right? Sorry. Anything to the 0 power is 1, right? So this to the 0 is 1 times this to the 0 is 1 times this to the 0 is 1. So if you wanted to predict the odds that someone had a malignant tumor, if they had 0, 0, 0 for those 3 measurements, that odds would just be 0.00003. Really small odds, right? Because they have really low measurements on everything else. When you plug in zeros there, and there, your predicted odds are just 0.00003. And if you want to convert that to a probability, right? Don't forget, you can do, to get from odds to probability, just do odds over 1 plus the odds. And since it's so close to 0, the probability is going to be really close to 0 too, right? So here's just a little function. If you're tired of writing odds over 1 plus the odds, you can write a little function that just takes the odds and then spits out the probability. Oops, sorry. And then we can say, hey, we'll give it the odds. I'll call it odds to prob, right? And then we can use it. And hey, this is the probability of malignancy if all those things are 0, right? Very small probability, right? And it makes sense. These things are all very positively associated with malignancy. Clump thickness, marginal adhesion, bland chromatin. So when they're low, the probability of having a malignant tumor is very low, right? What about these other coefficients though, right? So 2.592 for clump thickness. How do we interpret that? We know this intercept is the predicted odds when everything else is 0, right? When all the coefficients are equal to 0. Yeah, absolutely. You can totally use predict to do the same thing. If you wanted to, yeah, that's a good question. If you wanted to try it, just do, yeah, that's an awesome question. Just do predict and then say like clump thickness, new data equals data.frame, clump thickness equals 0, marginal adhesion equals 0, bland chromatin equals 0. Let me just do that, right? Might as well. Let's hop on the server. And let me grab that code so I can just run it. Grab this. Cool, let me clear this out. Yeah, so we can just run this code. And this is the same code that's in y'all's, that's in the worksheet for today. I don't know why that's still there. Let me get rid of that. Cool, so there's our data. Let me go ahead and run the model. Cool. Yeah, so you can totally just use predict to do this. I just want you to understand like what the model is, right? And like how it works. So if you wanted to just use predict, you can say predict. Let me make this a bit bigger so you can see. And move this over and scoot down. Cool, so predict fit2, we want new data equals data.frame. And let's say like clump thickness, thickness equals 0. What else? Marge adhesion equals 0. And then what was the other one? Bland chromatin equals 0. And then say type equals response. That'll give you the probability, right? Otherwise, it'll give you the logit. Cool. And that should be what we got. Oh yeah, when I did it by hand, I used 1.023 instead of 1.026. So, I mean, it's close enough, right? You'll get the same thing. For some reason, I didn't, I should have changed this to 026 instead of 023. I'm not sure why. I think it's just a typo. Still though, right? It's essentially 0.4 zeros and then 3, right, is what it would round to. Very, very small. That's a good question. Cool. So the coefficients, right? So interpreting this thing. So think about it, right? So every time, and again, the model was fit with clump thickness, marginal adhesion, and bland chromatin, right? So there's 3 things. So when you interpret this, that's controlling for marginal adhesion and bland chromatin. So for every 1 additional unit of clump thickness, that multiplies the odds of malignancy by 2.6 roughly, right? They go up like 160% each time you go up 1 clump thickness, right? So you can think of it this way. If you think of it on this scale, right? So if you're predicting the log odds before we exponentiated, if you go up 1 clump thickness, that adds 0.952 to the predicted log odds, which is increasing the probability, right? It's just 2 ways of expressing the same relationship. But that's confusing, right? Log odds are even more confusing than odds. So exponentiating them, interpreting them this way is better. So going up by, so once you've controlled for marginal adhesion and bland chromatin, when you increase clump thickness by 1, that multiplies the odds by a factor of 2.592, right? Imagine your odds if clump thickness is 0 is this, right? Your predicted odds if you have 0 clump thickness and 0 for everything else. If clump thickness goes up 1, then this gets multiplied by 1 of these, right? So it goes up by 160%, right? Or by multiplying it by 2.6, essentially. So either, whoops, sorry. That was weird. Sorry about that. So either way, right? But it's better to interpret in terms of the odds. That's how you're always going to see it done. And yeah, right, everything's significant. If we go back and look at this, everything's significant. All these are very strongly predictive of malignancy, right? Clump thickness, marginal adhesion, and they're all positive, right? Which is, if your log odds are positive, then that means your predicted probability, like the effect is positive, right? If any of these were negative, that would mean they would be having a negative effect on the probability. They'd be going down. So it's kind of nice. You can just look at the sign on the log odds scale. But it's better to look at the exponentiated coefficients. Cool. Neat. And the other coefficient interpretations you can do in the very same way, right? So it's really no different. Like literally, in this case, it's exactly the same. Controlling for, if you wanted to interpret this one, right? Controlling for clump thickness and bland chromatin, for every 1 unit increase in marginal adhesion, the odds of malignancy get multiplied by 1.8, or they go up by 80%, right? Every single time you increase marginal adhesion by 1, the odds of malignancy go up by 80% every time. 1.8 times 1.8 times 1.8 every single time, right? And so on. I'm torn. I don't know. Now let's keep going with this example. I was going to skip to the end, but let's keep going with this example. Classification is important, right? It's an important task in a lot of different domains. you usually hear about it most in like machine learning situations. So you've got a classifier, you know, let's say you build a classifier that tries to detect whether an email is spam based on characteristics of the email, like if it has a bunch of strange punctuation or, you know, certain keywords that tend to show up in spam, right? Then you can train it on some spam emails and see how well it classifies those, right? You can see how good of a job it does. And then you can set it loose in the wild once it's doing a pretty good job, and use it to actually classify in practice, right? Let me move me out of the way a bit. So it's a common thing, right? You want to classify, and it doesn't always have to be binary. Maybe there's like more than three or more categories, right? We'll talk about situations like that later, but it's best to just start slower and think about, you know, yes or no sort of binary classification. So classifiers, no matter what kind of classifier you're using, and you can think of logistic regression as a classifier, they're going to produce some kind of numeric index about how strong the prediction is. So logistic regression is great. It produces a predicted probability, right? Or a predicted odds or a predicted log odds, but they're all the same quantity, just on a different scale, right? So you could interpret either of those three as indexing how strong the prediction is, right? The bigger the probability, the more likely it is to be malignant, right? The bigger the log odds, the more likely it is to be malignant. The bigger the odds, the more likely it is to be malignant, right? All of them are indexing the strength of how, you know, how sure you are that this case is actually malignant or positive, right? Because that's the one we labeled 1. When I say positive, that's just the one we labeled 1, right? So like malignant or spam or whatever. It doesn't have to be a good thing. You just have to label one of them as 1, and that's the one you're predicting. But when you have these numbers that index how strong your prediction is, typically you want to like have a cutoff, right? Like maybe if my probability is above 0.5, I'm going to say this patient is malignant. If their predicted probability is below 0.5, I'll say it's benign, right? And you can imagine, like if their predicted probability is like 0.99, you're going to feel a lot better about saying it's malignant than if their predicted probability is 0.51, right? But there has to be a cutoff. And typically you leave that cutoff at 0.5. But today we're going to mess with the cutoff and see that we can generate some really interesting metrics for how accurately we are able to classify. Cool. So confusion matrices, right? This is the Wikipedia picture of a confusion matrix, like when you go to that article, and it's a really great picture. And it looks very confusing, right? But it's really not that bad. You've got your true positive counts, your false positive counts, your true negative counts, your false negative counts, right? So either you predicted malignant or benign, and the patient was actually malignant or actually benign, right? And these are just the counts in each of those 4 situations. And then all these other things out here in the margins are just other statistics you can calculate based on those frequencies, right? So it's literally just taking a frequency table of what you predicted and then comparing it to what the true value was. And that's it. We won't look at all these things, right? We talk some about accuracy, but really we'll be looking at the true positive rate called sensitivity, right? And some people call it recall. If you're typically working in like more of a machine learning setting, you hear it called recall. Then the specificity or the true negative rate, right? You want both of those to be high. You want your test to be very sensitive, right? You want it to, like, if there is actually a true positive, or if there is a positive, you know, like if someone's malignant, you want it to be able to classify them as malignant very well, right? And you also want it to be specific, right? So you don't want it to accidentally be classifying benign people as malignant very much, right? So you want to have a low false positive rate, which means a high true negative rate. These things are kind of confusing, right? It's kind of like thinking about type 1, type 2 error, except even more confusing, right? Because now we're talking about a couple different metrics, but these are 3 that we think about a lot. Yeah, and again, they're really not that bad to calculate. This thing looks nuts, but they kind of come naturally, and I think you'll see what I mean. So let's actually practice them. So if we take that model from before, and you can use it to get the predicted probabilities, right? So you can take that model and get the predicted probabilities. Just do model, whatever you saved it as, and then type equals response, right? And that'll give you the predicted probabilities. And then you can table those probabilities with the true values, right? So we can say predicted probabilities, if it's greater than 0.5, this will say true, otherwise it'll say false, right? And then we'll make that numeric. So the trues will become ones, the falses will become zeros. So when we predict 1, that means the predicted probability was above 0.5. And when we predict 0, the predicted probability was less than 0.5, right? And then you just look at a table of that by the true values. So 0 and 1. Cool. Did I name that fit or fit 2? That's interesting. I'm not sure. Oh, well, it's still working. Cool. So sensitivity, right? We can compute the true positive rate. So out of everybody who is actually malignant, how many did we classify as malignant? Well, so true 1 means they're malignant, right? So if the true value is 1, so there were 239 people who were malignant. We predicted 218 of them were malignant. So that's just 218 out of 239. So 0.912 here. Specificity is a true negative rate, right? So out of everybody who is negative, how many of those did we predict negative, right? So how many, out of everybody who's actually benign, how many did we predict were benign? Well, that's pretty high too, 428 out of 444, right? Cool. And then this, the precision. Precision, we won't talk about quite as much, but it's another interesting way to think about how you're classifying. So out of everybody who you classified as positive, right? Out of everybody who you said was malignant, what proportion of those were actually malignant? So that's just looking over here. So how many did you say were malignant? So we predicted 234 were malignant. And so 218 out of 234. So 218 were the ones who were actually positive, right? 218 of those 234 were actually positive. So that gives you the precision. We won't think about precision that much, but it's something to look out for. You don't want it to be, you don't want it to be very low. And we'll talk about, so the point of today is like, how can we combine these different ways of thinking about classification performance into one thing that like really works well? And that's where ROC curves come in, and like the area under ROC curves. Cool. So neat. So what we can do is we can take our model, right? And we can see like, this is just we can get the predicted logit scores or the log odds scores for everybody, right? And all that means is to go back to that original equation and plug in everybody's data and get the predicted log odds for everybody, right? So for person 1, maybe they had a clump thickness of 10, a marginal adhesion of 9, and a bland chromatin of 7. You plug those values in, and then it'll spit out, the linear equation will spit out the log odds, right? You do that for everybody, and then you can look at the distributions of log odds for people who are actually malignant and people who are actually benign. And remember, right, like if your log odds are greater than 0, that means the probability is greater than 0.5. So anybody who's to the right of this plot, right, anybody who's over here, we're going to predict that they're malignant. And notice, most of the time, they are malignant, right? There's a few people in here who are benign who are predicting malignant, but not very many. Most of the time, we're getting it right. There's 218 people in the red that are above the line, right? There's 21 people in the red who are below the line. So there's 21 false negatives here. There's 18 false positives here. There's 218 true positives. So this is just a way of illustrating the confusion matrix just by plotting the log odds, the predicted log odds for each of your 2 actual outcomes. And so it's doing a decent job, right? If it was doing a perfect job, what would this look like? There'd be no overlap, right? There'd be no false positives and no false negatives. There'd be 2 separate humps with no overlap. That would mean every person who was actually malignant was being predicted malignant or was above the line. And every person who was actually benign was being predicted benign or was below the line, right? This line right here. So this is just one way of like visualizing classification performance. Cool. So let's talk about, I want to be able to illustrate this a bit more simply because it's kind of confusing to look at these plots like this, right? So we had 3 variables. Let's do a little experiment. Remember principal component analysis, right? So our three variables, if you were to take the correlation, they're going to be strongly correlated, right? And they're also strongly predictive of the response variable, malignancy, right? So if they're strongly correlated, they're really redundant. And maybe we can express, how predictive they are of malignancy with a single variable instead. So again, this is just for illustration. I just want to take these three variables, clump thickness, marginal adhesion, and bland chromatin, and condense them down into one single variable that still accounts for a good proportion of the variation they can explain, or I mean, a good proportion of the total variation in these three variables. Is there one variable that, that can account for most of this variation? So I'm going to do a PCA and just grab the first principal component, right? Because it'll be the one that explains most of the variation. I won't even look at it. I'm just going to take it and grab it. Really, the goal is I don't want to mess with three variables because I don't want to plot three variables. I want to take one variable so I can just plot one, right? So this is cool. And you actually see this done in practice. You won't have to do this at all. This is just for illustration, but I think it'll make things a bit clearer. Cool. So then we'll take that principal component one, right? So I'm just going to run a principal component analysis, grab the first component, and save it in my data set as something called predictor. Then we'll run that logistic regression, predicting malignancy just from the first principal component. Because, right, if it explains most of the variation in clump thickness, marginal adhesion, and bland chromatin, then it should do a pretty good job predicting the response, right? Let's see if it does. So, cool. We'll just use this one predictor now instead of using all three. And we'll go ahead and get the predicted probabilities from this model, right? So we'll save those predicted probabilities. And now we can make a plot like this. So the whole point is, I just wanted to make a plot like this to show you what's going on here. This is the predicted probability as the predictor increases, right? So as your score on principal component one goes up and up and up, here's the predicted probability of malignancy. And we've got the points colored by whether the person was actually malignant or whether it was actually benign. So notice, right, most of the red dots are up here. Most of the time, people who are actually malignant have a predicted probability of above 0.5, right? Most of the red dots are above that cutoff, right? And most of the time, the benign people are below the cutoff, right? But it's not universally true. We can see that there are some malignant people down here who the model is only predicting has a predicted probability of malignancy of like 30% or something, right? So using 0.5 as a cutoff, it's what we're going to do. It's standard. You can see how it's, it results in false positives and false negatives. Because anything above that 0.5, anything above this horizontal line, we predict is malignant. Anything below that horizontal line, we predict is benign, right? But you can see that there are some benigns up here, these blue dots, that we're predicting malignant, right? Because they're above the line. And likewise, if we look down here, there's red dots, there's malignants that we're predicting are benign. So those are false negatives. We're predicting them negative, these red dots, but they're actually malignant, right? They're actually positive. And then up here, right, the benigns, those are false positives because they're actually benign, but since they're above that horizontal line, we're predicting that they're malignant. So this is just a cool plot to kind of illustrate this, right? And you can think about the false positive rate and the false negative rate, right? So the false positive rate, remember the sensitivity. So out of everybody who's malignant, what proportion do we predict are malignant? So out of all the red dots, what proportion are above the horizontal line? That's your true positive rate. The true negative rate, or the specificity, out of everybody who's benign, what proportion do we predict are benign? So out of all the blue dots, what proportion are below this line, right? Cool. So we're gonna break this down a couple different ways. First, let's just look at where it's 0.5. So we'll use a cutoff of 0.5, right? So the true positives are the red dots above the line, the true negatives are the blue dots below the line, and the false negatives are the reds below, the false positives are the blues above, right? And then we can get those counts of like how many are correct, true negatives, true positives, and how many are false negatives, false positives, right? That's just the confusion matrix. That's all it's telling you, right? So for example, if you take this and you say, hey, right, give me 1 if it's greater than 0.5, 0 otherwise, and then give me 1 if they actually have cancer, and 0 otherwise. And then you make this table, right? That's the same table as before. It's just that's just your confusion matrix, right? So try to map these numbers on to this plot right here. So for example, 21 were actually malignant, but we predicted 0. We predicted that they're benign, right? So where are those 21 here? They're actually malignant, so they're red, but we predicted they're benign, so they're below the line here, right? They're below 0.5. Our model would give them a low probability, even though they're malignant. So this 21 is telling us there are 21 red dots below the line. 21 actually malignant, who we predict are benign. The 16, right, are just the error in the opposite direction. Those are your false positives. They're actually, oh, hello, sorry. They're actually 0, so they're actually benign, but we're predicting that they're 1, that they're malignant, right? So these are the 16 blue dots up here. Cool. And then everybody else is correct, right? So the 0, 0s are your true negatives, the 218 are your true positives. And you can get the sensitivity and specificity, right? Just compute the proportion of the ones that are actually malignant that we predict are malignant. That's your sensitivity or true positive rate. And then the specificity, right? The proportion that are actually benign that we predict are benign, right? So out of all the ones where y equals 0, what proportion have a probability that's a predicted probability of less than 0.5? It's the same thing. You could also just literally do, this number right here is the same as if you were to do 218 out of 39. So there's 239 that are actually positive, and 218 were the ones we predicted positive that were actually positive, right? So 218 out of 239 should give you the same thing, right? So you can compute them the old-fashioned way too. This is just a quick way. Cool. But what if we change the cutoff, right? So imagine we move that horizontal line from 0.5. What if we change it to like 0.1? So anybody who has a predicted probability of above 0.1, we're going to predict malignant. And that seems kind of crazy, right? But we can do it. We can set that threshold to whatever we want. And this is just for illustration, right? Almost always you leave it at 0.5. But if you move the threshold, I just want you to see how the true positive rate and false positive rate change. Imagine what will happen, right? So if you lower that threshold from 0.5 to 0.1, you're going to be predicting a lot more positives, right? So out of everybody who's positive, you'll be getting more of those right. So your true positive rate is going to go up. There'll be more red dots. The proportion of red dots above the line is going to be higher because the line is lower, right? So your true positive rate or your sensitivity is going to go up, right? But what about the blue dots below the line, or your specificity, right? The ones who you're predicting benign, who are actually benign. That's going to go down, right? The proportion of blue dots below the line, there's going to be more blue dots above the line if you lower that line, right? So if you lower that threshold, you can think about it being more liberal about labeling a case positive, right? You're going to label anybody who's got a predicted probability of like 10% or more malignant. You're more likely to produce false positives, right? You're more likely to have benigns that are above the line. Actual benign people who you predict are positive or are malignant, right? But you're actually more likely to capture true positives, right? You're more likely to have people who are actually malignant being predicted malignant. So there's always this trade-off. The false positive rate and the true positive rate are always trading off, just like type 1 and type 2 error are always trading off. And you can see this, right? So imagine we lower that line. Just look, right? The proportion of red dots above that line now is pretty high, right? It's almost all of them. And the proportion of blue dots below the line has gotten worse, right? There's more blue dots above the line. So you can compute them now, right? You can see that the sensitivity goes up. So remember from before, the sensitivity was 0.91 and the specificity was 0.96, right? If you lower that cutoff, sensitivity goes up, right? The true positive rate goes up. more red dots above the line, but the specificity goes down. There's fewer blue dots below the line, right? So you can see like you're not making nearly as many false negatives, right? Like you're not, there's only 3 red dots that are below the line and you can't even really see them. They're kind of covered up. They're so dense in here, right? There's like almost 1,000, or how many points are there? There's like close to, 600-700 points. So you can't really see, but there are 3 red ones that are below the line, right? This is saying people who actually are malignant, who we predict are benign. And that's pretty good, right? But now there's 53 false positives. There's 53 that are actually benign that we predict are malignant, all these blue dots up here, right? So it's a trade-off. And same thing, right? So if we were to change the cutoff to something really high, right? So imagine instead we do the opposite. We raise that threshold to like 0.9 and we say we're only going to predict malignant if the model gives us a probability of 90% or greater, right? Think about what that does. So 90% or greater, there's going to be people who are malignant who don't have a probability that's that high, right? If we raise that line, the proportion of red dots above that line is going to get smaller, right? Because the red dots don't move around, the line just moves around, right? So the proportion of true positives gets smaller, right? We're going to have more false negatives. We're going to have more people who are actually malignant who are below the line, more red dots below the line. That's bad, right? But what about for the true negatives? The proportion of blue dots below the line. If you raise that line, the proportion of everybody who's malignant, or I'm sorry, out of everybody who's malignant, the proportion of people we predict, out of everybody who's benign, right, all the blue dots, the proportion of those below that line is going to go up, right? So we're going to make fewer false negatives. So it's the opposite of what we saw before, right? It's going to be more conservative about labeling a case positive. Basically, you have to be really, really sure that you're malignant if you're going to label it malignant, right? And that means a lot of the time you're going to be making, what am I trying to say? You're going to be making false negatives, right? Below the line, there'll be red dots below the line more often. So let me just show you the plot, right? Because it's easier to see. Instead of talking about it in the abstract is kind of confusing. But if you look at this now, right, you can see that, okay, most of the blue dots are below the line, right? So the true negative rate is good, right? We're classifying everybody below the line as benign, right? And out of all the blue dots, what proportion are below the line? Looks like most of them. There's a few up here, right? But our true positive rate is going to be lower. Out of everybody who's red, what proportion of those are above the line, right? So here sensitivity goes down. Remember before when we set the low threshold, the true positive rate was really high, right? It was like 0.96 or something. Now it's only 78% or 79%. Specificity though, the true negative rate goes up. So these things are always trading off. It's weird to talk about this though, right? So like, what's the point of this? We want to be able to use all the information here, right? Like about how our classifier is doing, not just at 0.5, but it'd be cool to look at it for every possible cutoff, right? And see like, what's the true positive rate? What's the false positive rate? Things like that. That's what an ROC curve does. It plots the true positive rate against the false positive rate. And it's really sort of a weird thing to do. It takes some getting used to, but once you're used to interpreting them, they're super easy to interpret. This is just showing you sensitivity and specificity for all possible cutoffs, right? So this is just showing the plot from before where we had a cutoff of 0.9. And remember the sensitivity was low, like 77% or something. What was that? 79%, right? And the specificity was high, like 90, almost 99%. And then here's where it was at 0.5. And then here's where it was when we set it to 0.1, right? So you can plot those against each other. Don't worry about it. It's just an extra kind of thing if you want. But here's an ROC curve. And this is you're going to see these curves a lot, especially if you go on to do stuff with medical data. They're very, very common. I'll even show you some real examples in just a second from journals. We can plot the sensitivity or the true positive rate against the false positive rate for every possible cutoff. So basically take that cutoff and raise it from, 100, or, lower it from 100% all the way to 0. And each time compute the true positive rate and the false positive rate. It's a weird plot, right? But they're going to look like this. This is actually a really good one. So if you get an ROC curve, an ROC, it's an old technique. It stands for receiver operating characteristic curve. People just call them ROC curves because that's a mouthful. But look, right? So imagine your threshold is 100%. Imagine you raise that line all the way to the top of the plot. What's your true positive rate? What proportion of the red dots are above the line? Well, if it's at 100%, there's no way anything can be above it, right? So 0. And that's what you're seeing here. So at 100%, the true positive rate is 0, right? And when you're at 100%, what's the false positive rate? The number of benigns that are above the line. It's also 0 because there's nothing above the line, right? So it's 0, 0. But as you raise it, so in a perfect world, like if your classifier was doing a perfect job, this thing would shoot straight up and it'd be like a right angle. This is actually pretty good, right? Let me show you. So this takes a while to like get used to. I have a couple GIFs in here that really are nice animations of like what this is trying to convey. But here's our situation, right? So here's all of the benigns. Here's all the malignants. Anybody above this line, we're classifying as malignant. So we got some false positives. Anybody below this line, we're classifying as benign. So we got some false negatives, right? Again, like I was saying, if you were predicting perfectly, what this curve would look like is it would go straight up and then it would go straight across. It would be 100% true positive rate for any given false positive rate, besides 0, right? So here's a nice demonstration of this. Take a look at this plot. I think it makes this a little bit easier to interpret. We're just moving the cutoff here. That's the same thing as moving that horizontal cutoff. You can move the log odds cutoff too if you want. That just shows you where you are on this, right? So watch what happens when this line gets to the very top. Okay, watch it. So it goes straight up until it hits part of that yellow plot. So right now, so it's going to go, that red dot goes up, up, up until that line crosses the yellow plot, right? And then it moves horizontally some, right? If there was no overlap between these two, it would go straight up and straight across. So that's sort of the goal. The closer this thing is to this this perfectly diagonal line here, the worse your prediction is. But this just shows you how this plot is generated, right? So like as you move the cutoff, where does this curve come from? And I'll show you how to do these by hand, but you really won't have to. Notice up here, it's saying the area under this curve is 0.85. That's literally the area under this plot. So notice, right, it's a square, it's a unit square. So if the AUC was 1, that would be perfect, right? It would be like a box. If it was this line, that's half of the box, right? This is doing better than that. So 0.85 isn't bad. In fact, it's pretty good. So this is just a way to think about how these curves get generated. You're just plotting the true positive rate against the false positive rate for every possible cutoff. And again, you won't do this manually. I'll show you how if you want, but you'll just use a package to do it. It's much easier. Cool, so here's a situation. Like imagine everybody who's malignant, you're predicting malignant, right? And everybody who's benign, you're predicting benign. So there's no overlap. There's no false positives, no false negatives. You'd get a curve just like this one. And the area under that curve would be 100%, right? The area under this thing, you get an AUC of 1. That's awesome. I mean, it doesn't happen in the real world, right? On the other hand, if your model is just garbage, right, and if it can't distinguish between malignant and benign at all, right, that means there's no systematic association between the predictor and whether it's malignant or benign. They're totally overlapping, right? If that's the case, you'll get something that looks like this, right, like a straight line. So if it's just random, right, like if your model can't predict better than a coin flip, you're going to get something that looks like this. And that area under the curve is 0.5. So basically the cutoffs, sometimes you'll get an AUC that's worse than 0.5, but it's weird if that happens. Typically, you're going to think about it as a range from 0.5 to 1. So this is a cool plot sort of demonstrating as your prediction gets better, right? As you're better able to distinguish between, you know, the true positive, or I'm sorry, the malignant and benign. Watch what happens to the ROC curve. The further apart it gets, the more that curve starts to look like a square, right? And then when they're totally apart, it's a perfect square. If they're overlapping, it's just noise around this horizontal line. So the AUC, everything boils down to that number, right? It does a really good job of telling you how well you're predicting. Way better job than just using accuracy or something like that does. And I'll explain why that is in just a second. I have to sort of demonstrate it because you won't believe me if I told you. Cool. Oh, here's this is something really recent about, so you can imagine, right, with the coronavirus stuff happening, people are trying to predict, in this case, respiratory failure. So among coronavirus patients, can we predict respiratory failure? And this person's looking at a potential predictor of respiratory failure. So respiratory failure is binary, right? Yes or no. And you can see down here, it kind of gets cut off. There's an ROC curve here. And it looks pretty good. Let me click on it just so you can see it a bit better. Wow, that's incredible. So what this means is, and I haven't read the paper or anything, I just searched for a tweet that was recent about ROC curves and found this one about coronavirus. But it looks like they found something that does a pretty good job at predicting respiratory failure among coronavirus patients, right? Because this is pretty darn close to, I mean, the area under that curve, and I'm sure it's reported in the paper, but it looks like it's going to be at least 0.9, right? It's very big. So that's interesting. And then also, here's an example of someone who's done a bit of snooping. So in JAMA, right, the Journal of the American Medical Association, they have a headline, and I think they're making a lot of this headline, right? So cardiogram could predict heart problems via smartwatches, right? So that's the headline. And I don't think that's making a crazy claim. It says it could predict, right? But this guy's saying it's an algorithmic failure, right? Because actually, when you look at the ROC curve, it's pretty bad, right? It doesn't look, it's pretty close to a straight line. You know, the AUC is going to be like 0.6 or something, right? So I don't think that's really overselling it. Like it could predict, I mean, that's pretty weak, but, you know, I don't think, I wouldn't go as far as to say that's an egregious overstatement of the evidence here. And again, I haven't read the paper. This is just something that came up when I searched for ROC stuff. So anyway, these things are used very frequently, right? And I still have to show you kind of why they're so much better than just using like accuracy or something like that. Cool. So, I mean, you could calculate this by hand. You don't have to, but in case you're curious, you can do a kind of a mechanical integration, right? So let's look at an easier example. So this is the ROC curve that you would get from lab, for example, if you're looking at predicting transmission type from the car's weight, right? And I'm plotting the true positive rate against the false positive rate for all cutoffs. And this is what it would look like. If you wanted to compute it by hand, you could literally just cut this up into little trapezoids, find the area of each trapezoid, and then add them all together, and that's the area under the curve, right? So you could take like, you know, the difference between the x values to get the base, and then you could get the height, or you can take this edge plus this edge divided by 2, right, to get the average height of the trapezoid, and then if it's a rectangle, it's just, base times height. But if it's this, you average those two little bits. Then you just add all those trapezoids together, right? So you compute this little area and so on, compute the whole area, add them together, and you're done, right? And you can do this manually if you wanted to, right? You could say, get those horizontal distances, the difference between the false positive rate for every cutoff. Then you can average the top and the bottom of the horizontal, the vertical lines, right? Average I keep thinking of it as a trapezoid like flipped over, right? Because you typically average the top and the bottom, average the sides. Then you can just sum up those trapezoids. And if you do that, you get an AUC of 0.93, which is really good, right? The area under this curve is 0.93. 0.93, right? So what does this mean? How can we interpret this AUC, like area under the curve? What does it represent? I like to think of it like this. This is the most useful way of thinking about it, in my opinion. So when you get the area under the curve, and I'm going to show y'all cutoffs, right? Like this is a common cutoff for a good one or a bad one or whatever, right? And they're just rules of thumb. But think about it this way. You can totally interpret it this way. So this number, 93.3%, that's the probability that a randomly selected person who has cancer has a higher predicted probability from your model than a randomly selected person that doesn't have cancer. So it sounds kind of weird, right? But basically you're saying 93.3% of the time, if you reached in to your data set at random and you grabbed somebody who had cancer and you grabbed somebody who didn't have cancer and you compared their predicted probabilities, 93.3% of the time, the person with cancer is going to have a higher predicted probability, right? Let me show you that that's actually true, that you can interpret it this way. So let's take our data set, randomly select one person who is malignant and one person who is benign. Then we're gonna see if it has, compare those two and see which one has the higher predicted probability. And then we'll do this over and over again, right? And then just average or find the proportion of the time that the person with cancer has a higher predicted probability than the person without cancer. And if they have a tie, in a situation where they have a tie, which will be weird, let's just give them 0.5. So basically, if malignant is greater than benign, we'll give it a 1. If malignant has an equal predicted probability to a benign person, we'll give it a 0.5. Otherwise, we'll give it a 0. Let's do this a bunch, right? So we'll do it 5,000 times. So I'm just going to reach in and grab somebody who, in this case, a car that's manual, and get their probability of being a manual, and then reach in and get a car that's an automatic and grab their probability of being a manual, and then compare those, right? And I'll do this 5,000 times, and then I'll just average those ranks, or those these numbers, these scores they got. And when you do that, it's 93.3%. So 93.3% of the time, when you compare, think about the cancer example if it's easier. When you compare someone who's actually malignant's predicted probability with someone who's actually benign's predicted probability, the malignant will be higher 93.3% of the time. That's what the AUC curve, you can interpret it that way. It's probably my favorite interpretation of it, because otherwise it's kind of an arbitrary number. So going back to the cancer example, right? Because the car example is silly. I just wanted you to be able to see those trapezoids because there's so many data points with the cancer example, it's hard to see them. The biopsy example, you can compute them by hand, right? So you can compute the AUC by hand, doing the same thing with the trapezoids, but don't worry about it, right? Like it's annoying to do that. There'll be little issues depending on how you, don't worry about it, right? You get 0.99 if you do it by hand, right? So 0.99, think about what that means. That's actually the proportion of the time someone with cancer will have a higher predicted probability than someone without cancer. 99% of the time. So that's pretty good, right? So for your project, and really for anything, like for the homework, you'll use a pre-existing function, right? You won't have to write your own function. You might go ahead and install this package. It's a handy one. So plot ROC, it just plots the ROC curve. It gives you access to this new ggplot geom called geom ROC. So you can say, hey, ggplot, I'll give it my data set, and then geom ROC, it wants the first thing to be the true outcome. So malignant or benign, right? 1, 0. And then M, the next thing, you'll give it the predictor, like, so either the predicted probability or the log odds, or if there's just a single predictor, you can just give it that predictor, right? You can give it the predictor variable if there's just a single predictor variable. Probably just give it the predicted probability. That's the easiest thing to do here. And if you do that and run it, it'll plot your ROC curve. And that's pretty good, right? That looks great. This is for the cancer example. And then once you've got this plot saved, right? And notice I saved the plot first. That's kind of weird, but that's the way that this function works. So if you want to compute the area under the curve here, you give this plot to a function called calc AUC. And yeah, it's going to spit out 0.99. So just like when we did it by hand, right? 0.99. Cool. So that's how you'll do it. It'll be much easier than doing it by hand. I just wanted to show you you could do it by hand, and like, you know, it's kind of a cute little integration by approximation. You just get those little trapezoids, right, and add them up. Cool. So just to show you, right, this is the ROC curve using information from marginal adhesion, clump thickness, and what was the other one? Bland chromatin. If we just use clump thickness, what do we get? So just using clump thickness, right? So I'll put clump thickness in there, just a single predictor. And look, it's much worse. So the AUC is 0.91 instead of 0.99, right? And you can see it's much flatter here compared to that one, right? So we're definitely getting better predictions by including those other things in the model, right? So here's some rules of thumb, right? So kind of like for the, you know, for the clustering where you looked at the silhouette width, you can think of, right, anything between 0.5 and 0.6 is pretty bad, pretty close to flipping a coin as your classifier, right? Not a good, you know, not good. Anything that's above 0.8 is probably pretty good, right? So you can cut them off into just these little, like, this 10%, this 10%, all the way up to, you know, if it's above 0.9, it's awesome. If it's above 0.8, it's between 0.8 and 0.9, it's good. Between 0.7 and 0.8, you know, fairish. Between 0.6 and 0.7, poor but not chance. And then, you know, close to 0.5 is just chance. Like, your model isn't predicting well at all. So why not just use accuracy, right? What's all this? Why do we have to go to so much trouble to get this AUC number? Because accuracy, right, that tells us the proportion of the time we get it right. So out of everybody, how many did we classify correctly, right? How many malignants did we classify as malignant? How many benigns did we classify as benign out of everybody? Why not just use that, right? Why make this weird curve and do this stuff? Accuracy has some problems. It can be tricked. So imagine a situation where you have a really rare disease. Say the disease only affects 1 in a million people, right? So it's really rare. Imagine that your wise guy friend or whatever says, oh, I have a really accurate test for that disease. And the test that this person is giving you just predicts zeros. It only predicts negative, right? So the test just gives you a negative prediction no matter what, always negative. It'll never predict positive. If you were to use that bogus test on this rare disease and look at the accuracy, it's going to be accurate 99.9999% of the time. It's going to get it right. It's only going to get it wrong for that 1 in a million people who have the disease, right? Most of the time it's going to be saying benign, 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 and the people are going to be benign, 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 right? It's only going to mess up for that 1 in a million. And so accuracy makes that test look really good when in fact the test is complete crap, right? It's just predicting 0 every time. What would happen if you were to use a classifier like that for ROC curves? So think about this particular situation, right? So 1 in a million have the disease, right? So there's 1 in a million that have the disease. If you predict 0 every time, your true negatives it's going to be perfect, right? For everybody who actually doesn't have the disease, this thing's going to label them negative, right? So your true negative rate's going to be 1. It's going to be perfect. But what about your true positive rate? Out of everybody who has the disease, how many do you get right? it's going to be 0, right? Because there's only one person who has the disease here in a million. And if you say negative every time, you're getting it wrong, right? So you have no true positives. We need to take information from both the true positive rate and the true negative rate and combine them, right? And that's what an ROC curve really does well. So let me just show you, right? So let's make this data up. Let's just put a random, so we'll create a vector of a million zeros, not a million zeros, 900,999 zeros, and then 1, 1, right? So this is a random 1 in a million. The 1 is malignant. All the other ones are benign. And let's say we use the wise guy test that just predicts benign the whole time, regardless, right? So just a million zeros. The accuracy is the number of times that what we predict equals the truth, right? Or just the proportion of the time. And that's, 99.99999% of the time. But if you were to compute the area under the curve, right, or the ROC curve for this, just give it the truth, give it the predictions, and watch the true positive rate versus the false positive rate as you change the cutoffs, right? And you get an AUC of exactly 0.5, right? And that's crap. It's detecting that the test sucks, right? Accuracy makes the test look like it's doing a good job, but it's a bogus test. Its true positive rate is 0, right? Its false positive rate, I'm sorry, its true negative rate is good, but its true positive rate sucks. And you can see that really clearly if you look at if you compute the area under the curve. Cool, so this is a good example of like how accuracy can kind of be fooled. Interesting question. So is AUC related to the p-values generated by the model? So like in our case, right? So yeah, the short answer is yeah, right? Like if your explanatory variables are predictive of the response, right? Then they're going to be significant, right? And your model's going to do a pretty good job of predicting. It's not perfect. It's going to depend on a lot of things. It's going to depend on sample size. It's going to depend on a lot of things. But in general, you can say, yeah, that's a good question. So in general, if your predictors are individually significant, your AUC is going to be higher than if you had the same data set and your predictors weren't significant, right? Because they're doing a better job of predicting. But it's more about how they predict together, right? So like how good is this model at giving probabilities above 0.5 when the person actually has cancer, right? But yeah, that's a good question. Cool. So that's most of what I had for today. I have a couple examples. The example from last time, but I really want to, since we have extra time, I really want to make sure I talk about the interaction stuff in the homework because it's a bit hairy, right? Interpreting those coefficients is already confusing. Throw an interaction in, and everyone's brain melts, mine included, right? So real quick, just to show you how this works from last time. Here's that example predicting admissions from GRE score, GPA, and rank. And with this example, once we interpret it, we'll also look at the ROC curve and the AUC for this example. And what you're going to see, actually, this has some bearing on the question that was just asked. Because in this example, individually, these things will be significant, but overall, it's not going to do a great job of predicting, right? So, the difference between saying, yeah, we're pretty sure that GRE score impacts admissions, and then being able to predict really, really well, right? If you have a big enough sample size, any little effect is going to be significant. So it's not a perfect correspondence, but I think what I said before is best. Like given the same data, if your predictors are significant, right? If they have really small p-values, then your model is going to be more predictive of the truth than if you have the same data set and your predictors weren't significant, right? But let's just see this, right? Because it is kind of a weird example, but it's a great illustration of the last question that was asked. So let's just predict admissions from GRE score, GPA, and then the rank of the undergrad institution, right? So rank 1 is like tier 1, rank 2 is tier 2, and so on, right? So a lower rank is better. And then go ahead and say family equals binomial, right? Because we're predicting admission, so yes, no. Cool. And then you can do co-F test or summary, it doesn't matter. And it'll spit out the estimates and then the p-values, right? So you can see that, yeah, everything's significant. So GRE impacts admissions, GPA impacts admissions, and those are both positive, right? So they both have a positive effect on admissions. And we can interpret, like, I mean, go back and check out the last slides if you want to interpret these, but you totally can, right? So controlling for GPA and rank, for every one additional GRE point, the predicted log odds are going to go up by 0.002, right? So you'd want to exponentiate that to say the predicted odds go up by whatever, right? But GRE is having a positive impact, GPA is having a positive impact. So rank, right? So rank 2 schools are less likely to get admission than rank 1 schools. Rank 3 schools are less likely to get admission than rank 1 schools, and rank 4 are less likely, right? So you can, just looking at the negative signs and the positive signs, you can already tell a lot. If you want a full full interpretation of every coefficient, check out the last slides. I really just want to focus on the classification performance. So we can use this model, right? We can say, hey, take this model we just ran, fit3, and use it to predict for every student their predicted probability of admission. And then we'll get the prediction. So we'll say if that probability is greater than 0.5, we'll say 1, otherwise we'll say 0, right? And then we can make a table of the predictions by whether or not they actually got in, right? So it looks like, oh, interesting. So the true negatives are great in this situation, right? So for everybody who actually didn't get in, so there's 273 people who didn't get in, right? That's the true admission is 0, so 273. 254 of those we predicted wouldn't get in. So the true negative rate is good, right? 254 over 273. The true positive rate, however, kind of sucks. So out of everybody who actually got into grad school, what proportion did the model predict? And again, we're using some variables that are pretty predictive, right? We're using GPA and the rank of the undergrad institution and GRE score. But even using those, the model is only predicting that 30 people would get in, but when in fact 127 people got in. So that's your true positive rate, 30 out of 127. And that sucks, right? That's really bad. That's like less than a quarter. I wish I had computed those, but you can see, right? That's not very good. We're making a lot of, in this case, we have a lot of false negatives. Students who actually got into grad school, who the model's predicting wouldn't get in. Because there's a whole bunch of other things involved, right? Like grad school is mostly about research, right? Depending on if you're going into depending on what kind of program, right? But this doesn't take research ability into account at all, right? It doesn't take lots of things into account. So if you look at a AUC curve for this data, just take the data, send it to ggplot, then we can say geom ROC, and we can give it the admission, so whether or not the person was admitted, and then the probability. Oh, did I save that in? Yeah. And then the predicted probability that they got in, and it'll plot this ROC curve for you. So this is whether or not they were admitted, and then this is what the model thinks the probability would be. And you can see, you know, it's not terrible, but it's not great, right? It's right on the cusp of poor, you know, it's like fair to poor. It's not a great predictor. It's better than chance, but not much, right? And this is just to show you, right? It's hard to predict admissions just from those 3 variables. So it's kind of a cool example, right? Because it looks like this model is awesome. It looks like, oh, wow, look at all those significant things. But when you look at how well it actually predicts admissions, that's why it gives you more insight into like how well you're actually classifying, right? Going back to that question.